The write succeeded in Virginia at 9 hours 41 minutes and 3 seconds, and the read in Frankfurt at 9 hours 41 minutes and 4 seconds said the row did not exist. Not an error. Not a timeout. A successful 200 OK containing an empty result set. The user had just changed their shipping address, watched the confirmation toast appear, refreshed the page, and got the old address back. They changed it again. Refreshed. Old address. They did this 4 times, then opened a support ticket that said, "In full, your website is lying to me." And the network was fine. That is the detail that makes this interesting. No partition, no packet loss, no failover, no incident. Every node healthy, every link up, dashboards green across 3 regions. The system was behaving exactly as designed, and the design was producing a lie. So the useful question is not what broke. Nothing broke. The useful question is, what did this system promise, and who decided that promise was acceptable? Most engineers reach for CAP here, and CAP cannot explain this. CAP says, when a partition happens, you choose consistency or availability. That is a true statement about a failure mode. But there was no partition. CAP describes a coin flip that only gets flipped during a network fault, and networks are fine the overwhelming majority of the time. Which means CAP is silent about the entire normal operating life of your system, the 99.9% where the interesting trade-off is still being made, silently, on every single request. That silence is the gap PACELC fills. The formulation comes from Daniel Abadi, who proposed it in a blog post in 2010 and then made the full argument in a paper 2 years later, and it reads as 2 conditional clauses. If there is a partition, choose between availability and consistency, that part is just CAP, absorbed whole. Else, and this is the addition, choose between latency and consistency. PACELC, partition, availability or consistency. Else, latency or consistency. Sit with the second clause, because it is the one that describes your Tuesday afternoon. Why should there be a trade-off at all when the network is healthy? Because consistency is not a property you have. It is work you do, and the work takes time. Concretely, your write lands on a node in Virginia. You now have a choice about when to tell the client done. You can acknowledge immediately, after one node has it, and replicate to Frankfurt and Singapore in the background. That acknowledgement costs you 1 local disk write, maybe 2 milliseconds. Or you can hold the client's connection open, ship the write to the other regions, wait for them to confirm, and only then say done. Virginia to Frankfurt and back is roughly 90 milliseconds on a good day. Physics, not engineering, that is light through glass across an ocean, and no amount of clever code makes the Atlantic narrower. So the trade is 2 milliseconds against 90. 45 times slower, to guarantee that a read anywhere in the world reflects that write. Nobody chooses that by accident. Somebody chose it, possibly years ago, possibly by accepting a default in a configuration file, and the address bug was that decision arriving late. Which reframes the incident completely. The system did not fail. The system spent 88 milliseconds of saved latency on every write, and the price of that saving was occasionally showing a user stale data. That is a purchase. The bug is that nobody knew they had made it. Now, the useful part of PACELC is that it turns vague architectural feeling into a 2-letter classification you can actually apply to a database. Every system gets a pair, what it does under partition, and what it does otherwise. Dynamo-style systems, Cassandra, RIAC, and Amazon's original internal Dynamo, the one from the 2007 paper, are PA/EL. Under partition, stay available and serve possibly stale data. Otherwise, favor latency, acknowledge on a quorum, or even a single node, and reconcile afterwards. These are built for the assumption that a slightly wrong answer now beats a correct answer in 90 milliseconds. Worth separating that from today's DynamoDB, which despite the name is a different design with a strong leader per partition, and does not belong in this box. Classic single master relational systems, Postgres or MySQL with synchronous replication, are PC/EC. Under partition, refuse writes rather than diverge. Otherwise, still refuse to acknowledge until the replica confirms. Consistency in both clauses, latency paid in both clauses. And then the genuinely interesting ones. Google Spanner is PC/EC, and it is the reason people misunderstand this whole area. Spanner offers external consistency across continents, which sounds like it has beaten the trade-off. It has not. It has paid for it in a currency most companies cannot spend: atomic clocks and GPS receivers in every data center, an interval-based time API, and a commit protocol that deliberately waits out clock uncertainty before acknowledging. Spanner does not avoid the latency cost of consistency. It buys the ability to bound that cost tightly with hardware. When someone cites Spanner as proof that consistency is free, they are describing the outcome and skipping the invoice. MongoDB is worth naming too, because it is tunable rather than fixed PA/EC by default in modern versions, and it moves depending on your write concern and read preference. Which is the practical shape of most systems now. The trade-off is not chosen by your database vendor, it is chosen by whoever wrote the parameters in your connection string. That leads to the part that matters more than the taxonomy. PACELC is usually taught as a property of a database. That framing is too coarse to be useful, because the choice is not made once at procurement time. It is made per operation. Take the address change. Reading a user's own shipping address immediately after they wrote it must be consistent, anything else produces the support ticket we started with. Reading the same user's order history from 4 months ago can be 100 milliseconds stale and no human could tell. Same database, same user, same request cycle, opposite requirements. A system tuned globally for consistency pays 90 milliseconds on the history read for no benefit. A system tuned globally for latency breaks the address read. Neither global setting is correct, because the requirement is not global. So the real design work is deciding which operations are latency sensitive and which are consistency sensitive, and then being deliberate about each. Most mature systems end up mixed: strong reads for anything a user just wrote or anything financial, fast eventual reads for feeds, listings, aggregates, recommendations, and analytics. There is a cheaper resolution to the specific bug, though, and it is worth knowing because it shows the trade-off is not binary. The user's complaint was not, "the global state of my account is inconsistent." It was, "I cannot see my own change." That narrower promise has a name: read your writes consistency, and it does not require synchronous global replication. You can satisfy it by routing that user's reads to the region that accepted their write for a short window, or by having the client carry the version it last wrote and requiring reads to be at least that fresh. The user gets a coherent story about their own actions. Everyone else still gets fast eventual reads. Cost, near zero extra latency. That is the shape of good work in this area. The naive reading of PACELC is that you pick a side. The skilled reading is that consistency is not one thing, it is a stack of increasingly expensive guarantees, and you buy the weakest one that keeps the promise you actually made to the user. It is worth naming that stack, because the middle of it is where most real systems should live and almost nobody shops there. At the cheap end is plain eventual consistency: write anywhere, read anywhere, converge later, no promises about what you see in between. One step up from eventual is the family of session guarantees, and the important thing about them is that they sit side by side rather than in a queue. They cost about the same and neither implies the other. Read your writes means you always see your own changes, other people's arrive when they arrive. Monotonic reads means time never runs backwards for a given reader, so a value you have already seen cannot be replaced by an older one on the next request. You can buy either one on its own, or both. That second one is surprisingly important, because the thing users actually report is rarely staleness, it is flickering, a value that alternates between new and old as their requests land on different replicas. Above both of them, causal consistency, which is effectively the session guarantees plus ordering across users. If one write happened because of another, everyone observes them in that order, so a reply never appears before the comment it answers. And only at the top, strong consistency, every reader everywhere sees a single global order of all writes, as though there were one machine. Each level costs more coordination than the one below it, and the jump in price is not smooth. At the leap from causal to strong is where you start paying cross-region round trips on every operation. The engineering mistake is treating this as a two-item list with eventual at the bottom and strong at the top, then picking strong because it sounds responsible. There is also a piece of arithmetic worth carrying, because it explains how quorum systems let you slide along this axis without changing databases. In a replicated store with n copies, if you require W replicas to acknowledge a write and R replicas to answer a read, then your read set and your write set are guaranteed to overlap whenever R plus W exceeds n. With 3 replicas, writing to 2 and reading from 2 satisfies it. 4 is greater than 3, and any successful read is then guaranteed to see the last completed write, while you still tolerate one dead node. That is read-write overlap, not full linearizability. With concurrent or partially completed writes it can still hand you something surprising. But for most purposes it is the fresh answer. Drop the read to a single replica and R plus W equals 3, which does not exceed 3, so reads may be stale but they are now local and fast. Same cluster, same data, different promise, chosen per query by 2 numbers. That inequality is the dial the ELC clause is actually describing. There is also a failure mode in the other direction, and it is the more expensive mistake in practice. Choosing consistency is not automatically the safe, responsible option. Synchronous cross-region replication means every write depends on a remote acknowledgement, which means your write availability is now the product of several regions' availability, and your write latency is bounded by your slowest replica. Add a coordination protocol and a single slow node degrades every write in the system rather than just its own. Teams that pick strong consistency everywhere out of caution frequently build something less reliable than the eventually consistent design they were afraid of because they moved the failure from occasionally stale read to write stop when a distant region has a bad minute. Stale data is visible and recoverable. Unavailable writes are neither. Back to Frankfurt at 9 hours 41 minutes and 4 seconds. The fix that shipped was not a database migration. It was read your writes for the account mutation paths. Session pin reads for 60 seconds after a write, while feeds in history stayed eventual. Address changes became coherent, P99 on read paths did not move, and nothing had to be replaced. The durable fix was a document. Every read path in that service now has a declared freshness requirement, written down, next to the endpoint, must reflect the caller's own writes, or maybe up to n seconds stale. It turns an invisible default into an explicit promise that a reviewer can check. So the shape of the thing. CAP describes a choice you make during a fault, which is rare. PACELC adds the choice you make when everything is healthy, which is constant, and that one is latency against consistency, because consistency is coordination and coordination costs a round trip you cannot argue with. The classification is per operation rather than per database, and consistency is a graduated set of promises, not a switch, which is why read your writes so often solves the real complaint at a fraction of the price of strong global consistency. 2 things worth sitting with. In the system you work on now, pick the read that would most embarrass you if it returned data 3 seconds old. Do you know, not assume, whether that path currently guarantees freshness, or whether it happens to be fast enough that the problem has not surfaced yet? And on your write path, if you are waiting for a remote acknowledgement, can you name what breaks when that remote region has a slow minute, and is that failure mode one you would choose on purpose?